Thanks to Thibaut and the Fruition team for inviting me. And it's really an honor to get to speak about some of my work as I'm just a lowly PhD student. I haven't finished yet, so it's really nice to get to share some of, I guess, my blood, sweat, and tears a little bit. And I talked to some people in the industry not too long ago, and they said, you know, at UC Davis, they really beat you over the head with this data. And I regret to inform that some of the beating will continue. So I do have some data on different varieties. I'm working jointly with Professors Mark Matthews and Larry Williams, so I have some introductory slides, and then we'll get into the meat. So one way that we know, this is common in plant physiology, how water is used, primarily in two ways. A very small percentage of it gets used in photosynthetic reactions. Most of the water, about 98%, maybe a little bit more, 99%, irrelevant. Most of the water gets transpired out of the leaf, so we lose that water. But both of these things happen at the same time, and they're very important for the development of the plant. Leaf transpiration, shown on the y-axis here, is very tightly regulated by the stomata. And on the x-axis, we see the stomatal conductance. So as the stomata open up and the conductance increases, which you tend to see, as transpiration increases. And similarly, as the stomata close down, conductance goes down, and transpiration out of the leaf decreases. Because of this really close linear relationship, we can use conductance as a proxy for transpirational water loss when we're making measurements. So we know that when the stomata are open, they have high conductance, we're losing water, and that when they're closed, they have low conductance, we're not losing water. However, closed stomata can stifle plant growth and development, including things like shoot growth. Thibaut mentioned a little bit about shoot growth. Also canopy development and berry growth as well. If the stomata close under increasing water deficits, then we can maybe use judicious water deficits when we're irrigating our vineyards to save a little bit of water and not impact important physiological functions of the vine. So we can diagram stomatal response to water deficits, and in this figure, the water deficits, and for the remainder of the talk, the water deficits are going to be given as a leaf water potential, as a measure of plant water status. So in this case, in this diagram, you see just a really straightforward linear response. Leaf water potential goes down. As you move to the left, the plant gets drier. Stomatal conductance goes down. The stomata close up. So we can say, let's say this is a typical response of a cultivar, cultivar A, for example. We could then say that it's to some degree sensitive to drought, insofar as the stomata close at a constant rate as the plant gets drier and drier and drier. This is a response that's commonly seen in the literature on grapes. You always see a linear response. Some people have documented other responses, and I'll show you something that I've seen a little bit different as well, depending on the variety. We could also encounter something like this response. Call it cultivar B. Its stomata stay open as the plant gets drier and drier until a certain threshold water status is reached right here. And once that threshold is reached, then the stomata begin to close down to curtail transpiration. We could say that this type of response is maybe a less sensitive response to drought when we compare it to cultivar A. We can think about these different responses between the cultivars in a few different ways. For example, cultivar A, simply put, maybe has a higher conductance, so maybe it has a higher potential to make more stuff, whether that stuff is growing more shoots or growing bigger berries or making more sugar or more acid or more color. On the other hand, it may use relatively more water under well-watered conditions and relatively less water when grown under water deficits. Irrigation management of this type of cultivar may be pretty straightforward. You cut the water back, the stomata close down, you give it water, stomata open up. Alternatively, cultivar B may have a lower maximum conductance, so it may have a limitation on how much it could potentially produce. For example, how large its berries could become, how much sugar it could make, etc. It won't utilize any more water at a higher water status, so keeping it well watered may be a waste. From another point of view, cultivar B may not show any effects of water stress until much higher levels of stress. Therefore, imposing a stress won't hurt productivity quite as much. ultimately, management of this type of response may require a little bit more precision initially, just so you can dial in the threshold and you figure out where that threshold is. So all of this, of course, leads to some interesting and important questions, at least I think they're important. Namely, are there really differences between cultivars in terms of stomatal response to water deficits? Also, is there a threshold for stomatal closure? Does this response change over time as the season goes forward? And finally, how does this response, how might this response affect berry development? So my experiment takes place at the Kearney Ag Center in Parlier, California, in the gorgeous Central Valley. And it's a small 1-acre parcel. It's originally planted by Dr. James Wolpert in 2004. It's a variety trial, 20 red wine grapes, all planted on the same rootstock, 1103P. There's 48 vines per row. There's 4 blocks. There's 12 vines per block. So it's a really nice opportunity. It's a small site. All the soil is very homogeneous, so no variability there. And if you've ever been to Parlier, I can assure you it is a fine community. Thank you. Here's the list of the cultivars on the left-hand side used in this experiment. We have several cultivars of Iberian origin, including Touriga Nacional, Tempranillo. We also have some Italians, both from the north and from the south of Italy, Bordeaux and Rhone varieties as well. And on the right, you'll see the source of the budwood. Very interesting stuff, I'm sure. Now, the 3 irrigation treatments that we had for the experiment, originally imposed in 2011 by my co-advisor, Dr. Larry Williams. The vineyard has been irrigated this way ever since, and to quantify plant water status, as I mentioned, we're using leaf water potential. Stomatal conductance measurements were made on the leaves just before we made the water potential measurements, so we're using the same leaf. And on the bottom, you'll see a diagram of what we expected the time course of water potential to look like throughout the season. So we have a late deficit treatment, which gets watered at 100% of ET before veraison, or from berry set until veraison, and then nothing, no irrigation until harvest. We have a sustained deficit irrigation treatment, which gets 50% of ET all season long. And we have an early deficit treatment, which gets no water at all from berry set until veraison, and then 50% of ET after veraison. Now all the vines are irrigated the same before berry set and irrigated the same after harvest. So here are 2 figures that show the seasonal course of leaf water potential in the top figure and stomatal conductance in the bottom figure, measured across all the cultivars. So the lines we see are the treatments. The solid black line on the left-hand side is when we impose the treatments, and then the gray blocks on the left and the right are veraison and periods of veraison and harvest, respectively. If you look in the top figure, the uppermost line is a non-stressed baseline leaf water potential, which is a calculated number. We can calculate that from relative humidity and temperature measurements taken in the field. And if you look at the solid black line with the squares, that's the late deficit treatment, for example. It kind of bounces along pretty close to that non-stressed baseline until veraison, and then it takes a dive to very low water status. And then, of course, we have the early deficit treatment with the solid circles and the sustained deficit treatment with the open circles, splitting off much like what we would expect. And you can see that generally the patterns between stomatal conductance and water potential throughout the course of the season are the same. And this is across all the cultivars. So when we plot stomatal conductance against leaf water potential, you get a lot of points. And as we move to the right, of course, the plants are getting wetter, conductance increases. We move to the left, the plants are getting drier, conductance decreases. Now, it looks like it might be a straightforward linear response, but there is quite a bit of variability in that middle section, sort of a bulge in the middle section of that group of data. And when we overlay colors for different cultivars, it sort of looks like a bowl of fruity pebbles. So there's a lot of different varieties, a lot of colors, and it's hard to make out what's going on and where are the responses that we're looking for. We can plot lines for each one of the cultivars to try and get a handle on what the responses are. Unfortunately, this doesn't really help us figure out what's going on. It doesn't really help to clarify the picture. One way that I figured that I could try and clarify this picture is by making groups. If the responses are similar, maybe I can group the cultivars together and then maybe get a clearer picture on a particular type of response. So for instance, I saw this group right away. These guys, as the plants got drier, they maintained a higher level of conductance. So I said, hey, that's one group. These guys right here, the conductance seemed to crash as the vines got drier earlier than the rest. And then, of course, we have the everybody else group right here in the middle. Here's a list of the groupings. As you can see, first of all, the numbers and the colors are just for your reference in the next few figures, just so we're oriented on the same things. Group 1, red. Group 2, green. Group 3, blue. Now, most of the cultivars, including Cabernet Sauvignon, for example, had a linear response. But there were two other groups that had distinct threshold responses. And I called them a sensitive response, which were the guys that dropped off early, and then an insensitive response, which are the guys that didn't drop off at all when the vines got drier. So when we see the same data again, we see the same data as I showed before, but now there's only 3 colors, and the colors are relative to the group assignments that I made. And we can see very clearly that we have that linear response group in the red line. We have that insensitive response, as I called it, group 3, the blue line. As the plants get drier, the conductance maintains. And then we have a sensitive group, the green line, where the conductance drops off very rapidly as the plants get drier. Here, the data points, I just removed them just so it's a little bit more clear. And what I've done here is to testing for statistical significance. Obviously, this is all very interesting, but if there's really no statistical difference, then what's the point? The curves here are bound in gray bands, and what those represent are 95% confidence intervals. And basically, wherever those bands are not touching, that's where the responses are significantly different from one another. And what you can see is that at high levels of water stress, all the way to the left, they're all the same. All the stomata are closed. When the plants are all well watered, all the way to the right of the figure, all the stomata are wide open, and there's no differences between any of the varieties. But it's really in that intermediate range of water status where the responses and the varieties actually separate out very nicely. And that's generally between about minus 1.7 on the low end and minus 1.2 megapascals on the high end. If you look at it another way, we have for each group their maximal conductance, let's say at the top here at minus 0.7 megapascals under well-watered conditions. And as you move down through the table with increasing water stress, what we see is a % reduction in stomatal conductance relative to the max. So at minus 1.2 megapascals, group 1 has lost about 1/3 of its conductance, while group 2, the sensitive group, has lost over 40%. Meanwhile, group 3, the insensitive group, has only lost about 15% of its maximal conductance. Further stressing the plants down to minus 1.5 megapascals, you see that group 1 has lost nearly 2/3 of its max conductance, while group 2, the sensitive group, has lost already 75% almost of its maximal conductance. And group 3 is still holding pretty strong with less than a 50% loss in maximal conductance at minus 1.5 megapascals. So what can we say about this? We can say that the cultivars separated nicely into 3 different groups based on their responses to leaf water potential. The significant differences were only found in the intermediate ranges of water status. Below minus 1.7 at very dry conditions, the vines are all the same, or the cultivars are all the same. Above minus 1.2, all the varieties were very similar as well, so no differences there at the ends. There's a linear response in group 1, different threshold responses for 2 and 3. And again, group 3 I labeled as the insensitive group, which maintained a higher conductance. And group 2 is a sensitive group, which dropped off very rapidly. When we look at this progression over time, so what we have here are the same 2 variables, conductance and leaf water potential, and they're plotted in 16 panels. Now, each panel represents a week of the measurements that I took. And in the very top left, we have week 1, for example. And as we move to the right and down, we're moving through the season. Now, what's interesting was when I first made this figure, I immediately noticed that the red lines, which represent just a linear regression line through the data, tended to flatten out as the season progressed. And what this shows is that not only does the maximal conductance of all of the varieties, this is across all the varieties, not only does the maximal conductance decrease as the season goes on, this would be represented by like the point all the way to the right on the red line, but the sensitivity to decreasing water status of the stomatal conductance is also decreasing over time. Each line in the previous figure has an equation, and you can take the numbers that represent the sensitivity to water stress and the numbers that represent the maximal conductance, and you can plot those over time, and you see the same thing, that the maximum conductance goes down over the course of the season, and the sensitivity to water stress, measured by leaf water potential, goes down as well. So then what I decided to do was I wanted to model certain values of leaf water potential to see what the conductance might look like over the course of the season if we tried to maintain a certain water potential. So at the top, you'll see minus 0.8 megapascals, in the middle, minus 1.2, and at the bottom, minus 1.6 megapascals. This figure is interesting because it illustrates two things simultaneously. First, the effect of leaf age on conductance. As leaves get older, their stomatal conductance is reduced, and this is a common phenomenon in plant physiology. It's very well documented in the literature. And the second thing that this figure shows is that the effect of water stress is much more pronounced on the conductance early in the season compared to late in the season. There's roughly an 80% decrease in stomatal conductance early on in the season, given the same difference of water potential, versus a 50% decrease in stomatal conductance at the end of the season. Given the phenology of canopy and fruit development in the vineyard, this might suggest that early water deficits might be very difficult to make up for later on in the growing season. So what have we learned from this? The stomatal conductance response to leaf water potential decreased as the season progressed, both in terms of max conductance and the sensitivity of conductance to leaf water potential. Stomatal conductance was significantly more sensitive to drought early in the season than it was at the end. As I said, 80% mean reduction early on versus 50% later. In terms of management considerations, I started to think about how we measure water status actually in the field, going out there. And I thought that maybe using a stomatal conductance or pyrometer might be very useful early on in the season, where it's a very sensitive measure of a sensitive indicator of water stress. But later in the season, stomatal conductance might prove to overestimate water stress in the plants, because you're getting a lower number for the same level of water stress measured with a pressure chamber technique such as stem or leaf water potential. And the physiological implications of this, of course, are very important, as the early part of the season is when there's a lot of that development that I was mentioning, berry growth, canopy development. So the early deficits are obviously going to affect vine growth, much greater than late deficits. And so this last figure's got a lot going on, so I'll walk everybody through it. There's colors and shapes and lines. So the shapes represent the different irrigation treatments. The circles are the ones that got no water before veraison. The squares are the ones that got, the squares are the irrigation treatments, the late deficit treatment that got a lot of water early and no water late. And then the triangles are the sustained deficit, which got the same rate of irrigation but all season long. We can see that as far as the shapes are concerned, they're all the early deficit dots, the circles, are in the bottom left-hand corner. And then the squares and the triangles, the ones that did get a little bit of water early on, are all fanned out to the top right. You can also see into the legend where it mentions the irrigation treatments that we have the average amounts of water applied as millimeters of ET for each treatment at the end of the season. That's the total that we gave them. You also have colors in this figure, and the colors represent the same groupings that I made earlier based on stomatal response. And what we see here is the sensitive group, the green line, has a much steeper slope down towards the bottom left compared to the other two. So not only, what? Oh yeah. This is the last one. So the green line, very steep, very sensitive. The stomata close early. The berry size is greatly reduced, much more so than the other two groups. Group 3, the insensitive group, is the least steep line. So the berry size is reduced less significantly than the other ones. So early water deficits, significantly reduced berry size compared to sustaining some water deficits early in the season. and this matches the stomatal modeling data, or the seasonal modeling data, excuse me. The sensitive group, the berry size at harvest, was most significantly affected by early deficits, excuse me. And the linear and the insensitive group, berry size at harvest, was a little bit lower at the end of the day, but it wasn't as sensitive, and that also matches the stomatal conductance data. Of course, I want to thank Thibaut again and Fruition for inviting me out, and of course, acknowledgments to my department, my graduate group, American Vineyard Foundation, and the California Institute of Water Resources. Thank you so much.